Question 7 is about rate of reactions. So first bit of the question, what is order of reactions? So order of reaction is basically the power to which the concentration of a particular reactant, the concentration of a particular reactant is raised to in the rate equation. And everything that is shown in the rate equation is involved in the rate determining step. So the power to which you raise it to is basically what you call the molecularity. Molecularity is basically how many molecules is involved in the rate determining step, which is the slowest step in the reaction. That's why they appear in the overall rate equation. Anyway, so this is question 7a part 2. Use the data in the table. So we're given a couple of data. I find it more handy if I actually have to copy down the data, because otherwise it really doesn't make sense at all if I just talk about it without copying this data. Obviously it's more tedious, but then without having to show on the actual paper, I think this is well, this is the next to best option really. So I mean, that's what we'll do with the with issues regarding the copyright things. So I don't want to land myself in problem again. So let's just stick with this. Doesn't matter. What is important is how we think about it. All right. So use the data in the table. So there's my data. Let me just move up a little bit so that we can have all the space we need. So there's that. And there's that. Oops, no, there's not a straight line. That's better. This is also better. Okay, move that down a little bit. Now that's better. Okay, so what do we know? We can see that. So at the moment, let the rate be rate constant, ClO2 to the power of A and OH minus to the power of B. If I compare, explain your reasonings for 2 marks. So compare experiment 1 and 2. If I compare experiment 1 and 2, you can see that ClO2 is constant. The concentration of ClO2 doesn't change. As the OH minus increases by how many factor? Increases by a factor of 4, obviously you can see. 0.120 divided by 0.030. Increases by factor of 4, as I'll show you right now. What happened to the rate? The initial rate also increases, as you could see, 10 to the minus 4 to 10 to the minus 3 by a factor of, well, you can show it on your calculator. This is just how you would explain it in terms of calculation. I get exactly 4 as well. So when I increase concentration by 4, I get the rate increasing by 4. So therefore, first order with respect to whatever is changing, and that is OH minus. So meaning to say B is equal to 1 because B is the order with respect to OH minus. Now compare the other ones. Just now I saw that, was it, let me see. So 0.30 in green and 0.030. So I'm going to go from 1 and 3. As the ClO2 minus ClO2 concentration increases, when the OH minus concentration increases, the rate again changes. So meaning it cannot be 0 order. So compare experiment 1 and 3. When the OH minus is constant, can't even write constant properly, and the ClO2 increases by a factor of 0.050 divided by 0.020, 0.050 over 0.020. I think that is a factor of 2.5. Yep. The rate increases also by a factor of 4.50 times 10 to the minus 3. Let me just write it down because I don't want to keep on referring to the table. Okay, so you can pop that into your calculator. And I get 6.25. So this looks like 2.5 square exactly, and therefore second order with respect to the ClO2, which is changing. So A, because A was the order I put in the right equation, so A is going to be 2, not 1. Don't know why I did 1 there. So 6.25 just now. This thing is equal to 2.5 square. That was what happened when I increase the concentration at 2.5. The rate increases by a factor of that square because it's second order. It's ClO2 to the power of 2. So the number A there is 2 there. Okay, so for that 2 marks, you should be able to do it pretty quickly. And which is why the next bit, question 7, A part 3, they want you to write the red equations. Based on the previous question, you have ClO2 to the power of 2 and then OH minus to the power of 1 there. Now, very common type of question, use your red equations and the data from experiment 1. So if you look at the questions, your data from experiment 1, before you do that, it's best if you rearrange your equation first, because there's the essence of mathematics instead of having to write it again and again. So our rate for experiment 1 is 7.20 times 10 to the minus 4 divided by the concentration of ClO2, and you have to square it because there was the order with respect to ClO2, and then I take the concentration of OH minus 0.030. So I'm gonna cut that, and we can do the calculations down there. Cut that, and we'll do the calculation down there. Okay, so 7.20 times 10 to the minus 4 divided by 0.020 square divided by 0.030. I get 60, but don't forget your rate has a unit. Your rate has a unit of mole per dm cube per minute in the table given for free. Okay, your concentration has mole per dm cube square, and then you have another mole per dm cube from the OH minus concentrations. Hopefully you can see the mole per dm cube and mole per dm cube cancel out, and you get minute minus 1 over mole square dm minus 6. And of course, that is not how you leave your final answer. You gotta express it in the simplified form, all in one line. So this looks better now. Mole minus 2 dm plus 6 minute minus 1. The unit of a red constant has no meaning whatsoever because it follows the red equation, of which whatever appears in the red equation with a certain powers, it appears like that. This is divided by that, so it's got mole minus 2. This is minus 6. When you have 1 over that, it becomes dm to the power 6. Minute minus 1 remains. It's not second minus 1, so be very careful. Always read your table very carefully. You get 1 mark for the unit. Part B. So question 7, part B is basically working with the graph, but it's talking about decomposition of the benzene diazonium. Remember earlier there was a question on organic chemistry. Benzene diazonium reacts with a large amount of water. You are going to get phenol, and you're going to get HCl, and you're going to get N2 as a gas. This HCl will dissolve in water, and this is a product that is soluble in water as well. Phenol is weakly acidic. They can mix with the HCl, no problem at all. The N2 will just escape as a gas as you warm this up to room temperature. They said draw the structure of the organic product. I have done the full balance equations, but the answer, the organic product is definitely just phenol. So you just need to draw the phenol. My phenol is really ugly, so let me try that again. Still pretty ugly, but anyway, I'll live with it. That was B part 1. Question 7, B part 2. I find it hard for me to do this question without having the graph, so I'll stop recording and I'll copy the graph from the actual question. So I'm back with this graph from the actual question paper. Don't ask me where I get it from. This could be just any graph that I can draw on Excel, obviously. Use the graph to determine the rate of reaction at 100 seconds. So you want it at 100 seconds and you want the rate of reaction at 100 seconds. This is a curve, so what you need to do is you need to draw a tangent at 100 seconds. It's a lot easier to draw it on a screen iPad because, well, in reality you just need a ruler and you can get a tangent at that point, which is 100 seconds. So this is at 0, 0. So I just need to read the amount in y, the change in y over the change in x. So the change in y then, this is 0 0.015, 0 0.016, 0 0.017. So there is 0 0.0175. So 0 0.0175 minus 0, y2 minus y1, x2 minus x1. So this is 210, oops, sorry, no, 200, 300. So it's 220, 240, 260, 280, 290. So this is 290 seconds. So 290 minus 0. This is second at the bottom. On top is mole per dm cube. So altogether, what you get is 0.0175 divided by 290. These are given to two significant figures, so it's wise if I give my final answer to two significant figures, 6.0 times 10 to the power minus 5. Don't forget unit, mole per dm cube per second. This is two significant figure for that 1 mark there. Question 7, part C. You want to sketch a concentration time graph for a zero order reaction. Zero order reaction. What does zero order means? It means that rate constant multiplied by something is zero order like that. It means rate is just like that. But that is rate relative to concentration. This is rate against concentration, will just be that. But what does that mean in terms of concentration against time? The reactant is still used up. Reactant is still used up. But it will be at a constant rate. Okay, meaning to say it will be a straight line plot with a gradient of k. Okay, so this is concentration and this is time. Is my graph a bit straight? Yeah, it's alright. My graph is a bit distorted. Let me try and draw that again. So I think it's still distorted. Anyway, doesn't matter. Okay, so concentration against time. What we'll get is we'll get a straight line plot like this. A straight line plot has a gradient which is constant, and this gradient which is constant throughout is going to be k, because the gradient which is constant gives me the rate. As you know, zero order reactions, the rate is just k. Constant gradient for concentration against time graph for a zero order reaction. Now use your graph to suggest how the successive half-life vary as the concentration decreases. Okay, let's talk about half-life. So if this is what you begin with, half of the concentration is roughly there. So, you know, that is going to be the time taken. That is going to be the time taken for the concentration, initial concentrations to half. Then I'm going to half it again. Half from the green point. Hopefully you can see that, you know, the concentrations going half there, the time there is not longer the same. In fact, it's getting smaller. If you don't believe me, I can go half again. So now you can see the black one is getting a lot smaller. So this is the third half-life. The one in pink was the second half-life. The one in green was the first half-life. Oops, I don't want to write first half-life. I just want to write first. From the first, the second to the third, the half-life is not constant because it's not a first order reaction. It's a zero order reaction. By using our graph, we can see that the successive half-life decreases. This is for zero order reactions. For first order reaction, the successive half-life will be constant because what you get is an exponential decay kind of curve. All right, so that's the end of that 9-mark question on rate of reaction, question 7.